Hi. In the second video for orbital motion, we'll talk about Kepler's second and third law and how Newton explained why those happen. Kepler's second law is that when planets orbit, they speed up and slow down in their orbit. His official language was a line joining the planet and the sun sweeps out equal areas in equal intervals of time. So in other words, if a planet moves along the outer surface here, and these three shaded almost triangles are the same area, then it will take the planet the same amount of time to move from P1 to move to P2 as it does to move from P3 to P4 and to move from P5 to P6. In other words, this and this and this will all occur in the same amount of time. And so if the amount of time is the same and the planet is covering a greater distance, then it's going to be moving faster. So if we talk about speed that you would drive in your car, if you travel 60 miles in 1 hour, you're moving a lot faster than if you travel 10 miles in 1 hour. And so this is like moving a greater distance in the same given amount of time. So another way of describing his second law is that planets move faster when they're closer to the thing that they're orbiting. Consequently, the planet is moving at its absolute fastest when it's at its perihelion position and its absolute slowest at its aphelion position. So once again, it's going to move faster from C to D than it is from A to B, but both of those will occur in the same amount of time. Let's take a moment and review Kepler's second law. So why is it that planets speed up and slow down? Well, once again, the answer comes from Newton. Newton's second law specifically tells us that why, and his second law is that force equals mass times acceleration. Keep in mind that acceleration just means changing speed or direction. So, mass is constant. Planets don't lose and gain mass willy-nilly. They're pretty well fixed on that. And so, if mass is constant and the planet is speeding up, that means that the force of gravity is changing. Well, that makes sense. Because when the planet is farther from the sun, its force of gravity goes down because of the distance. If its force of gravity goes down, then the acceleration has to go down. It's going to slow down. If the planet is closer, then the force of gravity will be greater because of the distance, and the planet's going to have to speed up. Let's take a minute and review. Another reason why planets change their speed has to do with an idea of angular momentum. Angular momentum is the tendency of an object to keep spinning, or in our case, orbiting. Now this gets a little complicated, but we're going to keep it simple. So angular momentum, in other words, let's call it a desire, even though it's not alive. The desire to keep spinning is affected by three things. And it stays constant, so if one thing changes, something else has to change in order to keep it constant. Mass never changes, so that means that speed and the distance the mass spread out on are going to change in order to keep the amount of angular momentum constant. So, as an object gets further away, the distance from which its mass is spread out, in other words, there's mass in the sun, mass in the planet, and when we talk about the mass being spread out, we care about how far apart is all of the mass involved in this scenario. And so when two objects are farther apart, the mass is more spread out than when two objects are closer together. And so when they're farther apart, the speed is going to have to slow down in order to make the same amount of angular momentum. If two objects are closer together, the speed is going to speed up in order to have the same amount of angular momentum. And the best example of this is a figure skater. Most of you have probably seen a figure skating routine, and they almost all end with the figure skating doing a fancy spin. And usually they start their arms are flying around and their legs are flying around, and then at the end they pull everything in real tight, spin fast, and then throw their arms up. When they do that, they stop. The reason why they do that, and you see, is that their speed is increasing and decreasing based on how far apart their mass is. When their arms are very, very spread out, their mass is spread out over a larger distance than when they pull their body in really, really, really tight. Finally, Kepler's last law, the third law, can be a kind of a beast mathematically, but it's pretty easy to figure out intuitively. So mathematically, the wordage is the square of a planet's sidereal period in years is proportional to the cube of the length of the orbit's semi-major axis. That's a mouthful. So period, in that language, basically describes how long it takes the planet to make one orbit. The semi-major axis, remember, is the average distance. So, what we're really saying for this is planets that are closer to the Sun take less time to orbit than planets that are further away. The mathematical relationship got tweaked a little bit by Newton, but for now, that's all we care about. So when we look at the planets, this should make sense. Mercury's orbit is much, much, much shorter than Neptune's orbit. Mercury's much closer. It orbits in 88 days. Neptune takes 164 years. So that difference has to do with their distance. So why is this the case? Well, that should be pretty intuitive to you as well. Greater distances, in other words, wider orbits, are going to take longer to travel. Additionally, when you're further away, there's less gravity, which means that remember, force equals mass times acceleration. Lower gravity means lower force, so you're going to be slowing down. Let's take a minute and review Kepler's third law.
So Kepler's third law is primarily a mathematical law, and it gives us the relationship between distance and the period. So in this question, it says that Saturn is 9.54 AU from the Sun. It asks us what the period is, in other words, how much time it takes to orbit. So we'll use Kepler's third law, which is p squared equals a cubed, and it's given us this value. A is our semi-major axis. It's given us that A equals 9.54 AU. So we can plug that in. So P squared equals 9.54 cubed. AU is our target unit, so we don't have to do anything to that. So the first thing we'll do is we'll cube 9.54, so P squared equals 9.54 cubed, which is approximately 868. And now my number in the calculator is 0.250664. I'm only going to write 25, but since it's in my calculator, I'm going to leave it that way and round at the end. So finally, to solve for this, I need to take the square root of both sides. And so then I'll get P equals the square root of 868.250664. And when I put that in my calculator, I get 29.466093, etc. I've only got 3 digits in 9.54, so I'm just going to round to 3 digits and say 29.5. Now, for period, my unit is years. So the answer is Saturn's orbit takes 29.5 years to complete.
Let's take a minute and review Kepler's third law. Finally, it's important to note out I've been mostly talking about planets and the Sun, but this applies to anything that does orbits. So our moon orbiting Earth, another moon like one of Jupiter's moons orbiting Jupiter, an exoplanet orbiting a different star, or even a man-made satellite orbiting Earth. Alright, let's talk about why we care about this stuff. So it's nice just to study astronomy, but we can do a lot of stuff with this information too. So number one, it explains why we have tides. If we understand gravity, we know why there's a larger force of gravity when the moon is close and when they're pulling in the same direction. It also gives us clues about the gravity in stars and planets. Remember that as planets form and as stars form, gravity is heavily involved, and as things contract, it increases the gravity, and we understand that now with Newton's explanation of gravity. It also helps us find objects. So for most of human history, we only knew about Mercury, Venus, Earth, Mars, Jupiter, and Saturn, because that's what we can see. Uranus and Neptune weren't discovered until we had better technology. So Uranus was discovered by accident with a telescope. And once we looked at Uranus, we saw, hey, Uranus isn't moving the way that we think it should. So there must be something else pulling on Uranus, and sure enough, they calculated it and found Neptune exactly where the calculations suggested that it would be, just like 1 degree off. It also helps us, right now we're looking at planet X, That's the idea that outside of Pluto's orbit and some of the inner Kuiper Belt objects, that there might be a large object, perhaps the size of Uranus, out in the middle of the Kuiper Belt, and that math is basically coming from the same thing that we figured Neptune out with, and that's calculating the orbits based on Kepler and Newton's work. Additionally, when we look at other solar systems, other places we're looking for where life could possibly exist, we basically use Kepler's third law to figure out how far planets are from the thing they're orbiting, their sun, and that helps us determine whether, if it's a planet, how far that planet is and whether or not it's in that zone where water can exist, or the habitable zone. Additionally, we can use this information to predict where celestial objects will be at a certain time, and so consequently that helps us send probes places. We can, in 2007, we launched a probe that just got to Jupiter in 2015, and that's because we could send it on trajectories, and we could use the gravity from planets to move it forward, and that's all possible because of our understanding of Newton, Kepler, and Brahe. Additionally, we can launch objects into space because we understand this. Without understanding this, launching something into space would be very difficult. And probably most important to your lives is that without this understanding, the satellites that we have that's powering our internet and our GPS and our radios wouldn't be possible. We have hundreds and possibly thousands of man-made satellites up there, and they'd all crash into each other and wouldn't stay orbiting the Earth unless we understood this material. Our last part of the discussion regarding orbital motion has to do with a little bit of a clarification. We've been talking about one object orbiting another, and that's not really what happens. So what happens is the two objects orbit around the center of mass. Where that center of mass is, though, varies greatly with the size of the two objects. We can see that really easy by looking at balancing an object. I have here two pencils. Both pencils start off at being fairly evenly weighted at either side. The eraser is going to be a little heavier, but otherwise they're fairly evenly weighted. If I try to balance the regular eraser that doesn't have anything on it, I'm going to need to put it pretty close to the center of the pencil. And that's because the center of gravity is basically right between the two. That would be like two objects that are relatively close in mass, like two stars that orbit each other. Both stars are going to orbit like this, orbit around each other. Conversely, if I have an object such as this pencil with a whole bunch of weight on one side from the rubber bands, when I try to balance that on my finger, I'm going to have to put my finger very close to where that weight is because there's a lot of mass over here. And so when it orbits, it's going to orbit around the center of mass. And although this side will be moving a little bit, it's the pointy side that's going to be doing all of the major movement. And so that would be like Earth and the moon, where the moon is orbiting around Earth, but as it does, Earth is making tiny motions. We see that even more the case with Pluto and its moon. Pluto's moon is about half of its size, and so Charon, the moon, is doing this, but Pluto's doing this. So it's kind of like a big orbit and a little orbit. If there's a humongous difference, as there is with a planet and a star, the center of mass is so close to the star, it actually lies within the star. And so that's how we get it looking much more like planets orbit the sun, because the planet's moving around a lot, and the sun is moving so little that it's just kind of doing this. It's just kind of making tiny, tiny circles, and so consequently we really don't notice it that much. You have these drawings in your diagram, and they're not remotely close to scale, but draw an arrow in and label it center of mass, and that will be the point in which they orbit. So the spots on the top will orbit each other. The ones in the middle will, the object on the left will orbit the object on the right, but the object on the right will move too. And on the bottom one, the smaller object is going to appear to completely orbit the larger, even though in reality the larger orbit is going to be doing this. Let's take one last review about the center of gravity. And that's it for our discussion at orbital motion. As always, come see me if you have any questions.